Hello, my name is Aleksandar Radojkovic and today Stefan Krivokapic and I will talk about Boyer-Moore algorithm and the variations using heuristics that we designed and implemented. Boyer-Moore is one of the fastest online pattern searching algorithms. It tries to pair characters from the pattern by matching the characters from right to left and making shifts by using heuristics. On this slide are the topics that we will cover. Bad character heuristic tries to align mismatched character from the text with the rightmost occurrence of the same character in the pattern, if it exists. If the character doesn't exist, we move the pattern behind the mismatched character. In this example, we see that A from the text isn't matched with the G in the pattern, but NA exists in the pattern, so we move 2 positions to the right and align A from the pattern with A in the text. Preprocessing saves the rightmost occurrence of a character of the pattern in a table, and when mismatch occurs, we look up in the table to see the pattern shift amount. The problem happens when the mismatched character in the text exists in the matched part of the pattern. In that case, we shift pattern just by 1 position. The heuristic saves only the rightmost occurrence of a character, while ignoring any other occurrences of the same character in the pattern. In our heuristic, we save all occurrences of a character in a list, in descending order by index. That way, we ensure that we shift the pattern enough so that the mismatched character from the text aligns with the next occurrence of the same character from the pattern, and not only the rightmost one. In that case, we don't necessarily move the pattern only by 1 place to the right, but we might make a longer shift. In this example, the bad character heuristic would move only by 1 position to the right, because the rightmost occurrence of A in the pattern is to the right of the mismatched A in the text. But our heuristic knows that A exists left of the mismatched character in the pattern, so we can move by 2 positions and we can skip 1 unnecessary alignment. Another optimization is that if the mismatched character doesn't exist in the left side of the pattern is shifted right after the mismatched character, while the original heuristic would shift only by 1 position. If more occurrences of the mismatched character exist in the pattern, we move to the rightmost one in the unmatched part of the pattern.
Hi, I'm Stefan and I will continue with the presentation. First I will say something about weak-good suffix rule specified in the original Boyer-Moore algorithm. The weak-good suffix rule keeps track of all the suffixes in the pattern. In this example, AC, we can see it occurring 3 times throughout the pattern. If the rightmost suffix gets matched but a mismatch occurs on the next character to the left, the weak-good suffix will check if the same suffix exists in the pattern and will align with the matched suffix and check the pattern match again. In this example, AC matches, but B doesn't match, so the pattern was shifted by 3 positions to the right and align the next same suffix AC. And of course that will fail also, because this C that precedes it is same as this C, which is of course different than this B. The strong good suffix rule, which has better performance, improves on that by checking the character before the suffix and will skip the next suffix if the preceding character is the same in both suffixes. In this case, the middle AC suffix will get skipped because the character C that precedes it is the same as the character C that preceded the suffix before. So the heuristic will move on to the next AC because the preceding character is A, which is of course different than C. If the match suffix doesn't exist in the pattern will try to match the prefix, meaning it will check the first few characters if they match with the suffix, and if they match, the match prefix will align the suffix in the text. If the prefix doesn't match the suffix, the pattern gets shifted by the length of the pattern. In this example, if these 2 ACs didn't exist, the heuristic will check if this AA, the prefix, is the same as the suffix AC, and since they don't match, the pattern gets moved by the length of the pattern. Our heuristic checks if the mismatched character from the text exists somewhere in the pattern right before the suffix that got matched. In this example, we check if the character B that precedes the match suffix AC in the text exists somewhere in the pattern before AC, so we effectively search for BAC. With this improvement, we skip checking if A plus suffix AC aligns with B plus suffix AC, and we save one alignment. In this example, such a combination of B plus AC doesn't exist in the pattern, so we move the whole pattern by the length of the pattern. To enable this behavior, we add a multimap where the key is the suffix and value contains the preceding characters for the suffix in the pattern and their location in descending order. When a mismatch occurs, we check the pair suffix entry in the multimap and then check if the list contains the mismatched character. If two or more mismatched characters are found, we align with the rightmost one in the unmatched part of the pattern. The complete Boyer-Moore algorithm first calculates the possible shift using bad character heuristic, and then also does it by using strong good suffix rule. The maximum of both possible shifts is taken for the next shift of the pattern. Our modified version of the algorithm does the same thing but uses our two heuristics for calculating the shift. In standard written text with normal alphabets and words, the bad character heuristic is enough for the algorithm to perform well. But in case we have large text and patterns but with small alphabets, like in bioinformatics where the alphabet contains only 4 letters, A, C, G, T, the good suffix rule performs better for large patterns because of possible repeating suffixes. On the next slide we will discuss the results. The unit of measure which we use for comparison of the pattern searching algorithms is the amount of skipped alignments. The naive algorithm doesn't skip a single alignment and always shifts the pattern by one position to the right, so the total amount of shifts it does is equal to the length of the pattern. For each shift larger than 1, we skip some alignments that the naive algorithm would check. Here we see that the original Boyer-Moore algorithm performs about the same like our proposed modification of the algorithm. Our modification will probably perform better for certain patterns where many suffixes with different preceding characters would exist. The trade-off of our heuristic is that we have more complicated pre-processing, and instead of constant time shift calculation, we have a linear time shift calculation that is in proportion to the length of the list in a hash table. The improvement would be using more optimized data structures for the hash tables. If you want to learn more about the Boyer-Moore algorithm or check the materials we used for designing these heuristics, you can check these links in the sources section of this presentation. Thank you for your attention.